Music is universal, regardless of your age or your background. Everyone loves music and everyone listens to it. But what actually makes us gravitate towards the music that we love? Why does one song sound perfect for a late night drive while another makes you want to dance? What actually connects us to the music that we love? The easy answer is genre. And yes, genre is useful, but it doesn't quite give us the full picture. For example, Sade and Chris Brown are both technically R&B artists, but a lot of their songs tend to feel completely different. The actual connection to our music is deeper than just a label. It lives in the acoustic properties of the sound, the tempo, the harmonic structure, the texture, the energy, the acoustic fingerprint of the track. The problem is, these properties are invisible to us listeners, and the platforms that we use to discover music, Spotify, Apple Music, don't really help. They use black box algorithms. They track your listening history, recommend tracks to you, but they don't actually show you why. The reasoning is hidden. This project takes the opposite approach. Instead of hiding the analysis, we put it front and center, giving listeners direct access to the acoustic data behind the music that they love. This leads us to the central question behind this project. Can non technical users, these are everyday music listeners with no particular background in music theory or audio engineering, meaningfully engage with acoustic audio analysis if it is presented in the right way? That question led to three core objectives. First, build a system that accurately extracts acoustic features from raw audio. Second, make those features interpretable, not just numbers on a screen. And third, use them to enable music discovery and comparison in ways that go beyond what genre labels and listening history alone can offer. The underlying design principle throughout was transparency. Every metric is explained, every calculation is visible, and in short, no black boxes. The first step was to look at what the experts had to say. Before writing a single line of code, I went through literature on music information retrieval and music psychology to get a better understanding of how acoustic properties relate to human perception. The most important framework I came across was Russell's circumplex model of effect. Proposed in 1980, this model suggests that all emotional responses to music can be mapped onto two dimensions. The first is valence, how positive or negative the music feels. The second is arousal, how energizing or calming it feels. Plot those two on an axis, and you get four quadrants. An upbeat track would sit up here, excited, aroused, delighted. A ballad would probably go down here, gloomy, sad, droopy. That's low valence and low arousal. A heavy metal track goes up here, tense, angry, alarmed. Something like a spa playlist, though, would sit right here, calm, serene, and at ease. What's powerful about this model is that it gives us a mathematical way to talk about mood. Not just this song is sad, but precisely where it sits in emotional space. The research showed me exactly which acoustic features predict human emotion. For example, arousal is driven by features like energy, the raw loudness of the signal, and spectral richness, how dense and wide the frequencies are. Valence is heavily predicted by whether the track is in a major or minor key, alongside its danceability. The system extracts 12 of these foundational metrics. It measures things like dynamic range, difference between the quietest and loudest moments. High dynamic range means the track breathes, it has peaks and valleys. Classical music tends to be very dynamic, for example. Low dynamic range means everything is compressed to the same volume throughout. And melodic clarity is how much of the sound consists of recognizable pitched notes versus unpitched noise or percussion. A clean vocal melody scores high, a drum break scores low. Instead of just staring at raw data, ClearNoise combines them into an acoustic fingerprint, allowing users to get a better understanding of each individual metric as well as how they come together. Now, let's see it in action. So now let's take a look at the solution in action. This is ClearNoise. This is the home screen. Because the platform is targeted at everyday, non-expert listeners, transparency is front and center. The landing page acts as an onboarding guide, breaking down exactly how the algorithms work in plain English before the user even signs up. It also has descriptions on how exactly to read the graphs, and all the complex metrics that are on the website are defined and accessible at all times through the navigation bar. So let's sign in and get started. The first thing we look at is how to upload a track. Here I click the upload box and select a track. Once the track is in, I can play it to confirm it's the correct one and hit analyze. Now, while the backend processes this file, the first of three technical pillars kicks in. The server uses Essentia, a powerful open source library, to run deterministic signal analysis, extracting those 12 acoustic features we talked about directly from the waveform. Once complete, we get an in-depth analysis of the track. I am presented with a number of visualizations to help me understand this analysis. The first is the spider graph, showing all the metrics of the track on a scale of 1 to 10. The stats grid showing the metrics and their actual values. Clicking on each gives us more information. The emotional profile based on Russell's complex, we can see that this track is tense. At the bottom, the waveform with different types of waves and descriptions on what they represent. Next, we look at the Discover screen, which has all the songs available on the website. For each, you can view its detailed analysis, add it to your library, or view it on the map. We have filters where you can sort or filter your results by any metric, and the semantic search, which uses the second technical pillar, a machine learning model mapping audio to text. This allows you to find tracks most similar to the vibe of anything that you search. You can also export these as a playlist. Compare screen allows you to compare up to 4 songs. You can add songs from your library or from your local computer. Each song has its metrics highlighted if it's the highest or lowest between all the songs. Analysis visualizations are overlaid for a visual comparison. The waveforms allow you to highlight to view one individual song as well. You can view a detailed side by side of all the metrics and click on each to get a deep dive for that specific metric. The library provides the same functionality as Discover, but with a personal touch, giving the user control. Finally, the map, an interactive 2D visualization of track similarity. It uses the third pillar, UMAP, to show the 512 dimension clap embeddings in just 2 dimensions. You can zoom and pan to explore, add concept markers that visualize mood areas, search and select tracks to view more information about them, view tracks that are just in your library, and select groups of songs directly from the map to add to your library or to export as a playlist. UMAP ensures that tracks that sound similar cluster physically together. So being able to select groups of tracks that are close together on the map allows you to create cohesive playlists seamlessly. I tested the platform with 11 target users, mostly aged 18 to 24, with an average acoustic familiarity score of 2.4 out of 5 before using the application, so genuinely non-technical users. Usability scores averaged 4.5 out of 5 across the 5 core usability statements, but the headline result was this. 100% of participants found that the system helped them better understand why a track sounds the way that it does, which was a core goal for this project. 91% of users found the explanations on the app very clear. Energy was selected by 82% of participants as their favorite metric. And importantly, every single metric received at least one selection in this question, so nothing was dead weight. 100% of users agreed that the emotional profiling at least somewhat matched the track's vibe, with zero complete mismatches. Overall, satisfaction was 4.73 out of 5 for the entire application, and every single user said that they're either likely or very likely to use a product like this again. Of course, context matters. 11 users in a narrow age gap is a strong usability indicator, but not a definitive baseline. There is also the novelty effect with new software, which tends to skew results positively. True validation requires a larger, broader demographic tested over a longer time period. Bringing it all together, let's look back at the project's three core objectives. First, accurately extract acoustic features from raw audio. Second, make those features interpretable for non-technical users. Largely met. Users rated their understanding after using the app highly, but feedback also shows that there's still work to do in improving explainability. Third, enable music discovery through novel techniques. Met. Semantic search, similarity maps, and acoustic filtering enable discovery through techniques that are simply not available on mainstream platforms. There are still limitations to address in future updates. The current rule-based valence arousal model could be improved with a trained neural classifier. Additionally, user feedback made it clear that direct streaming platform integration is the most requested next step for real-world use. ClearNoise started from a simple question. If music has a measurable fingerprint, why do we keep it hidden? The glassbox approach, transparent algorithms, plain English explanations, is a deliberate choice. In an industry built on black boxes, showing your working simply feels like the right thing to do. And of course, thank you for watching.